Next lecture will, I don't know, take place with John Chalker will present his lecture about many-body quantum at Gauss. And so he's a professor in physics department at Oxford University and also a senior research fellow at St. Hugh's College in Oxford. Yeah.
Okay. So first of all, many thanks to Michael Weigelmann for inviting me. This is my first visit to Slovenia, apart from some day trips. And the subject I'm going to talk about is more or less the one that the organisers suggested to me, and I hope I've interpreted it correctly. And so if things go well, then this should be complementary to what you're hearing from Alexei Kitaev on the one hand, and from Tomasz Prozan on the other. So I'm going to talk about many-body quantum chaos. I should say I feel slightly embarrassed to be talking on this subject in Ljubljana. There's a saying in British English that one shouldn't take coal to Newcastle, and I'm not sure whether that's a saying which is also familiar in international English, but in case not, I should explain that Newcastle is a port in the northeast of England, and in the Industrial Revolution, and in fact earlier, it was also the centre of a coal-producing area, and so the idea was that there was no reason to take coal to the source of coal for the country. And of course, in the 21st century, Ljubljana has been a great centre for quantum chaos, and so I feel a little embarrassed to be talking about that subject here. But anyway, I hope it'll be useful to you. And I'd also like to say that as I go on, I hope you'll ask questions whenever things are unclear, or if you want to try and add your own comments. So the plan for my 3 lectures is here. In this first lecture, I'll try and set the context a bit, and then I'll say some things about random matrix theory, and then I'll talk about this idea which is known as the eigenstate thermalization hypothesis. And in the second lecture, I'll talk about dynamics in many-body chaotic systems, and in the third lecture about how you can use a class of models known as random quantum circuits to do calculations and look at the quantities that I've introduced in the first 2 lectures. So the lecture today is on really some very old ideas, but since the subjects covered in this school are quite wide, I thought I should introduce these basics. So as a general thing, we're looking for universal features of generic many-body quantum systems, and it's worth unpacking that. So what does it mean to talk about a generic many-body system? Well, what I mean is a system that has only a few conservation laws, so for instance, energy and perhaps a few other conserved densities, or in fact, in the quantum circuits that I'll be talking about, it'll turn out there are no conservation laws whatsoever. So when we when we say this, when we say we're interested in generic systems, we're excluding, for example, systems of non-interacting particles, where the number of particles in each single particle orbital would be conserved. And we're also excluding beta-ansatz integrable systems, where essentially numbers of quasi-particles are conserved. And then we're also excluding many-body localized systems and excluding discussion, for example, of quantum stars. And we're also really thinking of systems that are where we're exploring behavior high up in the spectrum. So we want to exclude, for example, any low temperature regime where there might be a quasi-particle description of what's going on, which would take us back to something that might be interpreted in terms of free particles. So the kind of models that I have in mind, well, they're lattice systems rather than field theories. So we have a bounded many-body spectrum, and the simplest examples are probably spin chains, but the quantum circuits that I'll be talking about later on are more tractable examples. And I also stress universal features of these systems. So certainly some of these models might be quite far from a particular experimental system, although actually quantum circuits, one can probably realize with prototype quantum computers. But in general, we want to look at properties that are not too dependent on the specific system that we're studying. And these turn out to be, firstly, some statistical properties of energy levels and eigenfunctions. And then when we look at dynamics, if we want to have an aspect that's universal, then a natural thing to do is to focus on a description of the dynamics at long times and at long distances. And then, of course, as in many contexts, the idea is that a lot of the system-specific behavior would only show up on short distance scales and at short times, and by emphasizing long times and long distances, we get just the universal features. Okay, so what kind of things might we be looking for in the dynamics? Well, even at a classical level, if there are conserved quantities, then a description at long distances and long times might be in terms of hydrodynamics for conserved quantities. So, for instance, if you have a conserved density, you might start the system off in a state where you've got a concentration of the conserved density near the origin at time zero, and it might spread out perhaps diffusively at longer times, and you might have sound modes and so on as well. But that kind of aspect is not really the sort of thing I'll focus on, and one reason for looking at other things is that this feature quantum systems could have in common with classical systems, whereas my interest will more be in features that are specific to quantum systems. So for quantum systems, you can ask how they arrive at equilibrium, and the new aspect to that question in quantum systems is that the dynamics, of course, is unitary time evolution. And so if we think of an initial state in which, say, some particles of a gas are concentrated in one corner of a container and they spread out as time goes by, our understanding of this will be very different in a quantum system compared to within a classical description where we might think of chaotic trajectories and so on. So there'll be a specific account to quantum systems of how statistical mechanics can emerge when we start a system in a non-equilibrium initial state, an account that's specific to unitary dynamics. And another type of question that you can ask in quantum systems is to do with the dynamics of quantum information. In other words, really looking for aspects to dynamics which go beyond the hydrodynamics of conserved quantities that you might think about in classical systems. So, for instance, if we think about a system in a space-time diagram with space horizontally and time vertically, then we can imagine asking, and I'll talk in more detail about this later on, perturbing a system, say at the origin at time 0, and asking how the effects of the perturbation spread within a quantum mechanical description. So if we think in more detail about how we might characterize statistical properties of a system, or what it would mean to talk about the statistical properties, then first of all we can think about the Hamiltonian, or in the quantum circuits I'll be thinking of, I'll be interested really in a time evolution operator for Hamiltonian that varies periodically in time, so that I have a Floquet operator whose spectrum I can think about. But for a Hamiltonian, we might have some sequence of levels, and the question would be what statistical statements might we make about that sequence of levels. Or if we're thinking about eigenfunctions, then you might have a picture like this. So this is for a system in 2 space dimensions, and what's shown is a plot of the probability density associated with a particular eigenfunction. So the black regions, I think, are maxima in the probability density, and the white lines are nodal lines in the probability density. And the question would be, what are the right sorts of statistical questions to ask in this case? And more generally, what aspects are universal? So there's a long history of discussing questions like this, and the history really started in the context of nuclear physics in the 1960s, where people were measuring the energies of highly excited resonances in different nuclei, and these pictures are pictures for 3 different nuclear isotopes, and the energy runs vertically, and they're just plots of levels or excitations high up in the spectrum. And the question was what to say about data like this. And the basic point was that you couldn't repeat the kind of approach that you might have taken in atomic physics, for instance, when you study the spectrum of the hydrogen atom or other simple atoms, because in the first instance, it's not really possible to go from a microscopic model to a calculation of these energy levels. Certainly not with the computational resources that were available in the 1960s. And in any case, the sequence of levels is too specific to the fine details of the system, so that if you got fine details of the model wrong, you wouldn't match the experimental spectrum. So it became clear that asking about the exact energy levels was the wrong kind of question. Then there was a second inroad into interest in generic quantum systems when people thought about energy levels in simple low-dimensional quantum problems. So this is a picture of what's called a classical billiard. So you simply have a particle moving freely in two dimensions and being reflected from the walls of an enclosure, and these lines are just the trajectory of the particle, which has been followed for some finite length of time. Then the question was, what could you say about energy levels in a system like this? And in particular, are there simple things that you can say in the semi-classical limit when the wavelength of the quantum particle is much smaller than the size of the billiard? Then there was another source of interest in these generic quantum systems in the context of mesoscopic conductors in probably the mid-80s at its peak. So by mesoscopic conductors, I mean conducting samples which are small enough and cold enough that you can think of the electron wave function as being phase coherent over the whole of the sample. And typically, in fact, inelastic scattering as a result of interactions between the electrons is rather weak at these low temperatures. And so basically you're probing properties of individual electrons as they pass through the conducting devices. And the devices are irregular enough or with enough impurity scattering that at a classical level the electron motion would be chaotic. And then the signals of that chaos show up, for example, if you measure the resistance of the sample, which is what's plotted vertically, as a function of some external parameter, and it doesn't matter too much what, but in this picture, that's the magnetic field. So if you measure the resistance of one of these mesoscopic conductors as a function of magnetic field at a sequence of decreasing temperatures, then you see fluctuations in the resistance, which basically look as if there might be noise, but which are actually reproducible when you turn the magnetic field back down again. And these resistance fluctuations then turn out to be signatures of chaos. And then in the current context, there's a lot of interest in spatially extended many-body systems. And that comes, well, on the experimental side from the possibility of preparing and then watching evolve many-body systems that are well isolated from the environment, either in cold atom or trapped ion systems, or also in quantum information devices, which are being built on the way to quantum computing. And then there are several strands of thought from the theory side approaching these problems, both from condensed matter theory, from a quantum information perspective and also from high energy physics. So as you go through these various historical examples, then there have been different evolutions in the kind of problem that's studied. So in nuclear physics, you have a nucleus which you really think of as being point-like with no extended structure, and also with a Hamiltonian that for this kind of physics is perhaps not so certain. When you go to these low-dimensional systems, you have a problem with a very clearly defined Hamiltonian. When you go to mesoscopic conductors, then one way in which you're changing things is that you now have a possibility of at least two dimensionless combinations of length scales, because in a problem like a quantum billiard, then you really have two lengths, the wavelength of the quantum particle and the billiard size, so a single dimensionless ratio. In mesoscopic conductors, we have on the one hand the wavelength, the Fermi wavelength of the electrons, and then we also have some mean-free path for scattering either from the boundaries of the sample or from impurities in the sample, and that plays the same role as the size of the billiard system. But if you have impurity scattering, then you can have a much larger length scale, which is the size of the system, and you get new physics coming out from having these two-dimensionless length scales, the Fermi wavelength compared with the mean-free path, and the Fermi wavelength compared to the system size. So when we go to these spatially extended many-body systems, we're firstly dealing with many-body systems rather than the single-particle ones that we were dealing with here, and mostly in the context of mesoscopic conductors, but we're introducing spatial extent, which wasn't important in nuclear physics. So I've tried to explain some context, and now I want to talk first of all about random matrix theory and then about the eigenstate thermalization hypothesis. So these are both to do with ways of characterizing the system statistically, and the first of them is to do with talking about properties of the spectrum, and the second is to do with talking about properties of the wave functions. So going back to this point in the context of nuclear physics, the question was how to understand sequences of excitation energies in these complex quantum systems, different nuclear isotopes. Then there was a kind of revolution in point of view with the realization that what's worthwhile is to take a statistical approach. And there's a phrase which goes back essentially, I think, to Dyson, that what one should do is renounce all knowledge of the Hamiltonian. So this sounds completely revolutionary and possibly completely absurd. Rather than trying to calculate properties for individual systems, what you should do is think of some ensemble and try to calculate average properties of the ensemble. So there are different ways that you might construct an ensemble here. if you have a sequence of levels, then to some extent you can use the sequence provided it's sufficiently long as your ensemble. So, for example, as I'll discuss in a moment, you could look at successive spacings between levels and ask about their statistical properties. Or if you have one of the quantum billiard problems that I was talking about, you can look at some energy window and take levels from that window and ask about average properties. And in the context of the quantum billiard, you can do that in a rather clean way if you take the semi-classical limit, because when you take the semi-classical limit, you have a large number of levels within an energy window which is narrow enough compared to the center of the window that it's reasonable to expect the statistical properties to remain the same over the whole window. So on the one hand, you can think of ensembles in the literal sense of the data that you might have available to you. But the idea of random matrix theory goes a long way beyond that, because in these chaotic systems, we really can't hope to calculate the properties of an individual system. The whole point when we go from something simple like a hydrogen atom, which we can solve in the usual undergraduate way by separating variables, to something with fewer conservation laws, is that we can't actually hope to do calculations anymore except numerically. But the beauty of random matrix theory is that even though you can't calculate properties of individual systems, which would be these random matrices within the theory, what you can do is calculate properties averaged over the ensemble. And this gives an enormous amount of insight, and later on it's something that we can build on. And when I talk about random quantum circuits in my third lecture, that's still building on these insights from the 50s and 60s. So what kind of things might you hope to learn from this kind of approach? Well, it's going to be interesting if the properties of the spectrum, these statistical properties that I've emphasized, are actually linked in some way to the dynamics. And fortunately, it turns out that there are strong links. So, I mean, suppose we have some sequence of energy levels from one of those nuclear spectra or from a quantum billiard, and we've labeled them according to their magnitude. And then we can talk about scale variables, which are just the spacings between adjacent levels measured in units of the mean level spacing. And then, as I mentioned, this average could be an average over some window in the sequence. So a classic thing to do is to ask about the spacings of these nearest, the probability distribution of these nearest neighbor spacings. And that turns out to be interesting because you see clear differences between the behavior in regular systems, such as this rectangular billiard, and in chaotic systems, such as this stadium billiard. And the fact that they're regular and chaotic, of course, is reflected at a classical level by these particle trajectories in red, and you see that there are only 4 directions that the particles travel in the regular billiard as they get reflected from the walls, but in the chaotic system, as time goes by and you follow the trajectory for longer and longer, it goes in every possible direction and comes close to every point in the system. So the regular billiard, of course, is easy to solve quantum mechanically. You just use separation of variables and find eigenstates as standing waves in the 2 directions, and then the energies are the sums of the wave vectors squared for each motion in each of the 2 directions. But when you go high up in the spectrum, then successive eigenstates typically involve different wave vectors in the 2 directions, and successive levels are essentially uncorrelated. And what that means is that the sequence of energy levels is essentially Poisson distributed, so that the location of one level is independent of its neighbors. And when you work that through, that means that you have a Poisson distribution of the nearest neighbor level spacing. And if you do actual calculations of a sequence of levels, then you find a this Poisson distribution with a finite probability density for very small level spacings. Whereas when you do the same calculations but for a chaotic quantum billiard, then you find this distribution, which is known as a Wigner-Dyson distribution. And one of the key features is that there's suppression of the probability for a pair of levels to end up very close to each other compared to the regular system. So the first aspect of random matrix theory that I want to talk about is, in a sense, a toy example, because it just involves 2x2 matrices, but it'll give us some insight into the fact that within this Wigner-Dyson distribution, there's low probability for a pair of levels to be much more closely spaced than average. So we want to write down as a kind of toy version of Hamiltonian a 2x2 matrix, which should be Hermitian, since it's supposed to be the Hamiltonian for a quantum system. Then the most general 2x2 Hermitian matrix can be written as some coefficient times the unit matrix, and then a vector of 3 coefficients times the 3 Pauli matrices. And then, of course, the eigenvalues of this 2x2 Hamiltonian are some constant determined by the size of the unit matrix contribution, plus or minus a splitting, which depends on this vector multiplying the Pauli matrices. So going back to the spacings between levels, we have a spacing here of size epsilon that's determined by the magnitude of this 3-component vector. So if we say for this 2x2 problem that we want to work out the probability distribution of the level spacings, then what we should do is integrate a delta function on the level spacing epsilon with the magnitude of this vector A, we should integrate that over whatever our model is for the probability distribution of these three components of A. And then the key point is that when we think about the integration volume on which this delta function is satisfied, well, we're thinking of a three-dimensional integral, so this is the integration space, and the delta function is satisfied on the surface of the sphere of radius epsilon. So the integration volume, which contributes to this integral, is proportional to epsilon squared, and if this probability density for the three components of A is smooth near the origin, then that epsilon squared behavior will be the behavior of the probability density for small values of epsilon. And this example, I was thinking of general Hermitian matrices, but if we have time reversal symmetry, and we think of, if we have time reversal symmetry, then the Hamiltonian can be written in terms of real matrices, and thinking of the standard representation of Pauli matrices, that means we're fixing AY to be 0, and then instead of integration over the surface of the sphere, we have a two-dimensional integration space and integration around the circumference of the circle. And so with a constraint to real matrices, we have a probability density that's simply linear in the spacing between the levels, which is the form in the Wigner-Dyson distribution, and that's appropriate because these quantum billiard systems have time reversal symmetry. Okay, so when we go beyond that 2x2 problem, then we want to think of ensembles of random matrices of arbitrary size. And the idea, again, is that although we can't do calculations for individual examples of chaotic systems, we will be able to calculate properties averaged over an ensemble of systems. And in this case, the ensemble is an ensemble of random matrices. So if we think about n by n random matrices, and we think about sitting down to do a calculation, well, in the first instance, we want to define some kind of probability distribution, and we can simply take as coordinates the different matrix elements, and so on the one hand, we have real numbers on the diagonal, and if we're thinking about general Hermitian matrices, then we can think of one triangle off the diagonal and consider the real and the imaginary parts of the matrix elements as our coordinates. So a volume on the space of matrices will look something like this. And then we want to write down some distribution over matrices, and we want to do it in a way that doesn't favor any particular set of eigenvectors, because the whole idea was to renounce all knowledge of the Hamiltonian. And one way of writing down a distribution over matrices that doesn't privilege any choice of eigenvectors is to write it in terms of traces of powers of the matrix, because of course the trace of the matrix and of powers of the matrix is invariant under rotations. So a simple choice is to study what's known as the Gaussian unitary ensemble, where we take this measure and we weight it with a Gaussian, which has in its argument the trace of the square of the matrix. And when we write that out in terms of the components, then that means that each of these individual coordinates, the different matrix elements, is independently Gaussian distributed, apart from the constraint that because we're thinking of a Hermitian matrix, off-diagonal elements have to be related in the usual way by Hermitian conjugation.
I'm sorry.
Yes.
Why is the sign in the second term in the exponent?
Sorry, why?
Yes.
Yeah, okay. I separated out the diagonal and the off-diagonal terms, and that was basically my changing my mind when I was preparing the slide. So at one stage, I mean, one choice would be to take only these independent coordinates, and in that case, the sum would be over I less than j, but in that case, it would have a factor of 2 in front of it, and that somehow looked ugly to me. So I take your point that I could have simply kept only this term and had a sum over all I and j. And incidentally, the sign here is wrong, is a mistake. Yeah, the basic point is that we start with this trace of h squared, and then we expand it in terms of these coordinates. And when we do that, we see that each of the independent coordinates is Gaussian distributed. Thanks. So another possibility would be to think not about Hermitian matrices, but about unitary matrices. And in this whole context, that's a very natural thing to do because, of course, unitary matrices will appear in the context of time evolution. So that's something that I'll want to take up in the context of random unitary circuits. And in the case of unitary matrices, since the space of unitary matrices is compact rather than non-compact as it was in the case of Hermitian matrices, you can simply have a distribution which is a constant over that space, so that the ensemble is invariant under any rotation you choose. Because we avoid the Gaussian factors, this is an especially simple thing to study. So we can write down these random matrix ensembles, and now the question is, what would we like to know about them? And we constructed them. We constructed them precisely so that the eigenvector distribution was trivial. I argued that it was natural to take the probability distribution to involve traces of powers of the matrix so that our choice of basis is unimportant. And that means that each set of orthonormal set of eigenvectors will appear in the ensemble with equal weight. And so the thing that's interesting is the eigenvalue distribution rather than the eigenvector distribution. And here I've talked concretely about Hermitian matrices, but just as in the 2x2 toy example, we could also think about systems with time reversal invariance where we know that we could find a basis in which the matrix is real, so we could do the same thing here. So we could also, we could think either about Hermitian matrices or real symmetric matrices, and we could either think about unitary matrices or orthogonal ones. And there's a third choice in the context of random matrices, which I'm not going to talk about, which comes up when we have time reversal symmetry and levels which are all twofold degenerate because the system has total spin, which is half-odd integer. But I'll leave that on one side. Okay, so in this context of n by n random matrices, the way in which level repulsion comes about is essentially as a Jacobian that comes in when we change variables from the joint distribution, which I've talked about for the entries of the matrix, to a joint distribution which uses as coordinates the eigenvectors and the eigenvalues. And as I said, the eigenvector distribution is trivial, and so that factorizes out, and we can integrate over eigenvector orientations. And I'm not going to talk about the process of working out this Jacobian, but the effect that it has is to introduce a prefactor to this Gaussian. So you remember we had a Gaussian involving the trace of the square of the matrix, and if I introduce eigenvalues E1 to En for this n by n matrix, then this is the trace of the square of the matrix. And the Jacobian prefactor involves powers of the separations between different pairs of levels, with that power being 1, 2, or 4, depending on which of these symmetry classes we're talking about, with beta equals 2 corresponding to generic Hermitian matrices, and beta equals 1 corresponding to orthogonal matrices where we've imposed time reversal symmetry. And if we go to the case of n by n unitary matrices and stick with unitary rather than orthogonal matrices, then, well, the eigenvalues, of course, are complex numbers on a unit circle, so we might use the eigenphases as our coordinates. And once we've done this change of variables from the matrix elements to the eigenvalues, then the joint distribution is particularly simple because we no longer have this Gaussian factor. We simply have the Jacobian with, in this case, this power beta being 2. So now, in this effort to understand random matrix theory, on the one hand, we've made enormous simplifications because we've got rid of the eigenvectors of the matrix, and we're just focusing on the coordinates in the problem that we're interested in, these energy levels. But we've still got a complicated problem because we have to understand this joint distribution. And it's also useful to pause at this stage and think about what useful information we can get. And to do that, it's worth thinking about scales in the level distribution. So if we think of one of these random matrices, then there'll be some gross density of states if the size of the matrix is large, which would give us some function of energy like this curve, and then there are individual energy levels. And so we can think of different energy scales, and the smallest scale is the spacing between individual levels, and the largest scale is this bandwidth, which is of order n times the individual level spacing, although of course the level spacing itself may vary as you go across the band. So, coming back to this question of universality, the behavior of the random matrix on the scale of the bandwidth will probably be specific to the particular model that we're studying, and so possibly not something that's so interesting, at least as far as getting insights into generic systems. But there's a wide range of energies if the matrix is large, on which we can expect to find correlations that are universal and which are relevant beyond the specific random matrix model. So it's correlations on these scales much smaller than the bandwidth, but potentially, if the matrix size is large, much larger than the level spacing, which are what we're interested in. And at the same time, although we've simplified the problem in getting to this joint distribution, it's still a complicated one, and it's actually as complicated as any model of an interacting classical gas in statistical mechanics, in the sense that we have a probability distribution that depends on the coordinates of all of the levels, just as in statistical mechanics we'd have a probability distribution that depended on the coordinates of all of the gas particles. And in fact, of course, there's a precise correspondence with classical statistical mechanics, because since this is a probability distribution and therefore non-negative, we can simply take the log of it and put it into an exponent, and this beta is conveniently labeled to look like an inverse temperature. And so it's like a 1D gas with these particles, if these Z's are the eigenvalues of a unitary matrix, then their coordinates around the unit circle. And we have a repulsive interaction between the gas particles, which is just the log of this modulus without, yes. So when particles come close together, minus the log gets larger and positive, and that's the sense in which it's repulsive. So what do we want to know? Well, we can switch patches from the z's to the particle coordinates, the eigenphases around the unit circle, and we can think of the particle density for a particular realization of this random matrix as being a sum of delta functions. And in the usual way, as if we were talking about a gas in statistical mechanics, we like to understand few-point correlators. So we could think about one-point correlator, the two-point correlator, and higher-order quantities. And in fact, the one-point correlator is trivial because we have translational invariance as we move the particles around the unit circle. If we multiply all of the z's by the same phase, then that phase disappears when we take the modulus. And so the particle density is just the total particle number divided by the circumference of the circle. So the two-point correlation function is the lowest interesting quantity. And I want to talk about how you can at least get an idea of the behavior, and then I'll mention how you can do exact calculations as well. So the kind of thing that we'd expect is, well, whoops. Firstly, this two-point correlator, remembering that the density is a sum of delta functions. If we set the two angle arguments, density arguments, equal to each other, then we get a delta function contribution to the two-point correlator at the origin. So that's what this spike represents. And then secondly, as we go away from the origin, because we've got repulsive interactions, if there's a particle definitely at one point, say the origin, then the probability to have a second particle nearby will be reduced because of this repulsion. But if we go very far away, the two-point correlator should reduce to the square of the one-point correlator, and that's this constant on the sketch graph. So how can we understand that? Well, a natural thing to do is to write the interactions in terms of the particle density, which is really a sum of delta functions. So you're just reproducing this sum here. But then, since the energy only depends on separations between particles, we can diagonalize the interaction by taking Fourier transforms and introducing Fourier components of the density, which I'm writing as rho tilde of t. So t is an integer labeling the Fourier components of this Fourier transform. And when we write the interaction energy in terms of these Fourier components, then it's diagonal with the Fourier transform of this log interaction as the coefficient. And if you think about taking the Fourier transform of the log with, of course, a maximum for the value of z, because the particles are on a circle, then just by power counting, the Fourier transform varies with t, like 1 over t. And then to go further, well, as I was saying, we have the interaction energy written in this form, quadratic in Fourier components of the density. If we could simply say that the Fourier components of density were the variables we were dealing with in the classical statistical mechanics problem, we could simply solve the statistical mechanics problem by doing Gaussian integrals. Now, of course, actually the coordinates in the classical statistical mechanics problem are the positions of these energy levels or gas particles around the unit circle. But if we think about Fourier components of the density on scales much larger than the level spacing, then it's reasonable to indeed think of the Fourier components as being approximately independent variables. And if you do that, then the ensemble average of the square of a given density component is just the inverse of the coefficient in the energy. And since we've argued that the Fourier transform of the energy goes like 1 over t, that means that the fluctuations in a given Fourier component of the level density varies linearly with t. And then if we go back to the energy space, we have to take a Fourier transform again, and again by power counting, if we think of a Fourier transform with t dt, then that translates to 1 over energy separation squared as a correlation function. And if you don't follow this approximate route, but do the exact calculation, then the result that you get looks like this. So the thing to focus on is that the suppression of the density as you approach zero separation goes like 1 over s squared. S is a scaled version of the theta that I had before, just as it does in the calculation I outlined. But the effects that are missing are a modulation which has a period set by the mean spacing between the particles. So you've got a slightly crystalline array of levels, and apart from the density fluctuations, the periodic variation in density associated with this kind of crystalline arrangement, the main thing is that you have a 1 over s squared suppression as you approach small level separations. So I've given an exact result, and this is for the case beta equals 2. You can work out exact results in the other cases, but they're more complicated. I thought for the simplest case, I would leave you as a kind of homework exercise an indication of how you can do the calculation rather simply. And the point is that in what I've described, we thought of understanding this as a statistical mechanics problem in one dimension, but an alternative way of understanding things for the case when beta equals 2 is via quantum mechanics. And in point of fact, you can think of this probability density as being the probability density associated with a wave function, and that wave function is simply a Slater determinant, because if you expand out this Slater determinant, then you get something whose square vanishes when pairs of particles come together as a consequence of parallel exclusion, just as this probability density vanishes. So if we want to think about the properties of this Slater determinant, then we should just remember that the coordinates here, which are coordinates of the different particles raised to different powers, these are just plane waves around the unit circle. And so for each of the particles in this Slater determinant, we're filling up orbitals with different angular momentum around the unit circle. And the lowest orbital has angular momentum 0, this has angular momentum 1, and then we go on up to maximum angular momentum of capital N minus 1, where capital N is the number of particles in this Slater determinant. So that's simply a filled Fermi sea with a particle density corresponding to the mean level density that I argued for before. So if we want to calculate this two-point correlator, then in the quantum language, what we have to do is simply work out this two-point correlation function, and the standard techniques of creation and annihilation operators make it easy to do that for this field Fermi seed state. So if you do that calculation, then when you take the large n limit, you'll get back to the result that I had on this slide. Okay, so the picture there is that by thinking about random matrices, we can characterize at least one aspect of the system of chaotic quantum systems that has a chance of being universal. That's the behavior of eigenvalues. And in the calculation, I switched between energy and time. When I talked about time there, it was just a convenient way of diagonalizing the interaction. But it's also useful to think in the energy and time domains more generally. And so what I'm discussing here is the energy domain in the way that I talked about when I discussed the band of a random matrix and the different scales from the bandwidth down to the level spacing. But if we simply introduce time in the usual way in quantum mechanics as h bar over energy, then we can also talk about a time domain. And then, of course, the arrow has to run in the opposite direction because small energies correspond to large times. And then one of these scales, the smallest energy scale, translates to what's known as the Heisenberg time, the longest time scale that we're likely to be interested in, Planck's constant divided by the level spacing. And larger energy scales translate in the corresponding way. And I'm going to use terminology which wouldn't be appropriate if this is just a bandwidth, but will be appropriate later on. In the setting of mesoscopics, we talk about a timescale which is known as the Thales time, and random matrix behavior applies in a window, well, from the up to the Thales energy or from the Thales time to longer timescales. And if we think about the results that I talked about for level correlations in the time domain, then we're thinking about a unitary matrix, which might, for example, be a time involution operator. And so, again, we have eigenphases, and I'm writing a time argument in explicitly. And a quantity that it's convenient to think about is the spectral form factor, which is simply the Fourier transform of the two-point correlation function of the level density that I was discussing earlier on. If you take that level density rho of theta and Fourier transform it and take the modulus squared, then this is what you come to. And of course, we can get exactly this quantity by taking the trace of this evolution operator and the modulus squared, because the trace would be a single sum over these eigenphases, and then we take the modulus squared, we get a double sum and one set of eigenphases because of the modulus comes in with the other side. So if I replot the results that I was talking about for level correlations in unitary matrices from the circular unitary ensemble, then the result that you get looks exactly like this. So I emphasize level repulsion, and the effect of level repulsion is to reduce the amplitude of density fluctuations, especially at large scales. Since this spectral form factor is the modulus squared of the amplitude for density fluctuations, that spectral form factor is reduced at small values of t, corresponding to large scales in energy. And then to understand the plateau at large values of t, well, if t is much bigger than the Heisenberg time, then the contributions to this double sum from terms where the labels n and m are different from each other. Yes?
Maybe it's not k of t as defined in the slide, but the one where the trivial contribution, which is n squared, is subtracted, because otherwise it should be n squared that equals 0.
Yeah, okay, I'm happy with that. I guess in my mind I was leaving off the t equals 0 term. But yes, of course I agree.
Why there is an absolute value on the trace?
Sorry,
Why there is an absolute value on the trace of that?
Well, I just mean so that is the trace, and then this is the absolute value squared. So then I'm just saying that this is is that all right? Yeah, I mean, it's not excluded that there are other misprints in the slides, but I think that's okay. Yeah, so I was saying that the fact that the spectral form factor is small at small t, that's corresponding to there being small amplitude for density fluctuations on scales much bigger than the level spacing. And then what I was going on to say is that this plateau at large values of t, you can understand because at large values of t, the terms in this sum, apart from the diagonal one, will have independent random phases, and so when we average over an ensemble, they're averaged to 0, but the diagonal terms in the sum are each 1, and so if we have a sum from 1 to n, we'll get a contribution of n from those terms. In the context of the previous slide, the Heisenberg time is h bar over the level spacing, or in these units, the level spacing was 1 over n, or 2 pi over n, so the Heisenberg time here is simply n. Okay, so the third thing that I want to talk about today is statistical properties of eigenstates, and in particular the eigenstate chapelization hypothesis, which is an idea for describing what these statistical properties are in generic many-body quantum systems. So, to give some context, the picture that I showed before of the probability density of a specific eigenfunction was in the context of quantum billiards. And actually, in that context, we have a conjecture for how to think about the eigenfunctions, which is really based on this picture of trajectories. So the point is that if you follow the classical trajectories of a particle in this billiard for a long time, then at a given point, at successive times, you'll find the particle going past you in all possible directions. But of course, since reflections from the wall are elastic, the speed of the particle each time it goes past will be the same. And so the idea is that you should be able to think about the eigenstate as being similar to a random superposition of plane waves. And in each of the plane waves in this superposition, the wave vector will be the same, but the orientation will be different. So a random superposition of plane waves, given that the wave function, the eigenfunction should be real, will be a superposition of cosines with different phases for the different cosines, different amplitudes, perhaps Gaussian distributed, and different orientations, but the same magnitude for these wave vectors. And then you can think, for example, about correlation functions built from eigenfunctions. For instance, the correlator between the value of the eigenfunction at the origin and the eigenvalue at some point R, and average this over, well, some appropriate ensembles. So it could be an ensemble of billiard problems with slightly different shapes for the perimeter, or it could be an ensemble of eigenstates over some energy range, or within this form for eigenfunctions as a random superposition, it would be an average over these coefficients in the superposition and over these phases. And when you do the average over coefficients and phases, then what you end up with is simply the zeroth order Bessel function of the wave vector times the scalar separation between the 2 points in the correlation function. And that is a good statistical description of these sorts of eigenstates. So the question really is, what's a many-body version of this, and what would be the implications? And the eigenstate thermalization hypothesis gives a way of thinking about that. So, for example, to have a concrete system in mind, we could think of some sort of spin chain, perhaps with random fields applied at the different sites, but these need to be weak so that we're not in a many-body localized regime or even close to it. And one advantage of having in mind random fields is that then we automatically have an ensemble of systems, and averaging over the ensemble is something that we could do by averaging over the fields. So what we'd like is an analogue of Berry's random wave conjecture. And there's an obvious way that you could get it if you go to a gas of dilute hard spheres and study this in the semi-classical limit, then you'd be back to a many-body version of this billiard problem. But one difficulty with that is that that kind of many-body problem is essentially impossible to treat numerically, and numerics has been a very useful way of understanding things in this area. So in order to have something that we can apply to a problem like this disordered spin chain, we need to think in a different way.
Question.
Yes.
Why isn't dilute hard spheres many-body problem similar to the billiard single particle? What's that?
Well, if we had non-interacting particles, then sorry, let's start again. If we think of of classical trajectories in this high-dimensional coordinate space, then if we sit at a particular place in that space, we'll have the trajectory going past us multiple times if we wait long enough, and presumably successive times that the trajectory, many particle trajectory passes us, the velocities will be different because the particles will have scattered in between, but the total kinetic energy will be conserved because it's a conservative problem. So what I'm saying is that the 3n component vector will be of the same magnitude but directed in different directions each time. So we could write down an analog of the Berry conjecture where this R is in the 3n dimensional space and the K is a 3n dimensional wave vector, and its magnitude is fixed in exactly this way. And we take random amplitudes in random places. And I didn't put it on the slide, but actually, so Nikki did work that out, and the first corrections to the high temperature limit reproduce what you ought to find according to whether the particles are fermions or bosons, and you symmetrize or anti-symmetrize the wave function appropriately. But I'm not sure that it'd be possible to push that further, and you certainly can't apply it in systems which you can also treat numerically. Okay, so we want to be able to talk about the eigenstates and their properties in generic systems, but without having plane waves as a basis to fall back on. And the basic idea is that suppose we had two rather similar systems with Hamiltonians HA and HB, and they're different, for instance, by us having chosen slightly different values for these random fields. Then something that we could do is express the eigenvectors in the second problem in terms of the eigenvectors in the first problem. And the spirit is that if the two problems are similar, then this should be a physically appropriate basis. And the picture is that the eigenvectors in the second problem will be some kind of quasi-random superposition of the eigenvectors in the first problem. So I don't think there's a single clear-cut derivation of the eigenstate generalization hypothesis, although there are various plausibility arguments. I think the best thing to do is to state it and explain why it's useful, and then I'll perhaps come back to at least a consistency test. So rather than discuss the whole eigenfunction, the idea is to think about particular observables, say a spin operator at a given site in a spin chain, and to talk about properties of matrix elements of that observable between different eigenstates, many-body eigenstates in the system. And the statement is basically that there's a large non-fluctuating contribution to these matrix elements and a small fluctuating contribution. So the large non-fluctuating contribution is diagonal, and it depends only on the it depends smoothly on the energy of these eigenstates. So we can introduce coordinates which are the average of the two eigenstate energies, which I'm calling E, and the difference, which I'm calling omega. This non-fluctuating part of the matrix element depends smoothly on the average energy. And then there are some fluctuations, and the idea is that they can be written in this form. So firstly, there's a 1 over root n, and the idea is that n is large, and so 1 over root n will give these fluctuations some small amplitude. And then there's some envelope function, which depends on the average energy of the pair of eigenstates and on their separation. And then these two prefactors multiply something which is random, and R is just a random Gaussian matrix with average 0 and variance 1 for its matrix elements. And of course, some constraints. So if O is a Hermitian operator, then this should be a random matrix, should be a Hermitian matrix. And correspondingly, there's a constraint here relating F with omega and F with minus omega. And the size of this fluctuating piece, it's basically n is the number of states in the many body system that are relevant at a given temperature in a given energy window. So if we think of the Boltzmann formula for entropy as being k log omega, well, so Boltzmann's constant is 1. The exponential of the energy is just the number of states that are relevant at the energy that we're considering. Okay, so I've explained what the hypothesis is, and the question is, what does it do for you? Well, if we put the system in some generic state, then of course it won't be an eigenstate, it will be some superposition of eigenstates, with the states in this superposition perhaps drawn from some reasonably narrow energy window, as determined, for example, by the sorts of energy widths that you would have in contact with a heat path. And then one question is, how does statistical mechanics fit in with this? Well, the average of an operator will, of course, be an expectation value in this state. And you might think that the expectation value would depend on all of the expansion coefficients here. But if statistical mechanics is to hold, then we'd like it to depend on the expansion coefficients only via the expectation of the Hamiltonian. And the part of the eigenstate thermalization hypothesis that involves these diagonal elements is basically, well, the fact that these diagonal elements only depend on the average energy of these two states tells us that it doesn't matter which particular set of expansion coefficients you use to build a state in a certain energy window. The average of a local observable will be fixed by the average of the Hamiltonian, up to these fluctuations which are small. And it also tells you things about the dynamics, because if you think, say, about the autocorrelation function of an observable, then that will involve this off-diagonal contribution to the eigenstate thermalization hypothesis, and basically this envelope function encodes the autocorrelation function. Okay, so I think I've probably used up all of my time. I have a bit more to say about the eigenstate thermalization hypothesis, but I think I'll have plenty of time to cover that in the lecture tomorrow. Are there any questions?
There's no questions. Thanks.